Hello everyone, I'm Mohammad Farhan Soumik. I'm currently a computer science PhD student at Southern Illinois University Carbondale. I'm here today to present our work having the title Development of a Hand-Down Vibration Syndrome HUPS Detection Tool for Construction Workers. This work is a collaborative research work between Colorado State University and Shin Lab of Southern Illinois University Carbondale. Let's start our presentation with introduction. Primarily caused by prolonged use of vibrating handheld tools like jackhammers and grinders. These kinds of tools can be found in different sectors, but they are mostly prevalent in construction sectors. HARPS has multifaceted impact on human body. It damages vascular, neurological, as well as musculoskeletal systems of body. HARPS possesses economical as well as physical toll on both workers and employers. Now, symptoms. The most prevalent and common symptoms of HUPS is the continuous tremor in hands that the workers feel, then the numbness of fingertips, tingling, reduced grip strength, etc. Now, there has been lots of research done to detect HUPS properly, but the limitations of the current existing systems is that they're highly dependent on wearable sensor data. And the problem with wearable sensor data is that they're susceptible to noise. So a small noise can have huge detrimental effect on the whole detection mechanism. So if the goal of our research is to get out of this overdependence of wearable sensor data and use deep learning and to create a better system. Let's move on to the objective sections. The first objective of our research work is to build a lightweight, deep learning based tool to detect hubs from hand drawings. Our design model has to be lightweight because we want to deploy them on mass scale on edge devices to make them easily accessible to users. Number two, providing HUBs assessment in real time to workers without involving any wearable sensors. As I mentioned previously, the main purpose of this research work is to get rid of the over dependence on wearable sensor data for HUBs detection. We want to do that by using drawings, hand drawings. Number three is the most important point. HUBs and Parkinson's disease has some symptomatic similarities. We want to utilize that symptomatic similarities between HUBs and Parkinson's by using spiral and wave drawings. Number four, creating a user-friendly, easily deployable, that's why our model has to be lightweight, system possible to be used by workers with minimal training. So workers with minimal training can use the system. Number five, focusing on workers exposed to vibrating tool, monitoring their conditions through regular drawing-based assessment. These are our objectives. Now let's move on to our related work section. Our related work section can be divided into two categories. First one is the clinical and sensor-based approaches, and the second one is the machine learning-based approaches. Let's start with clinical and sensor-based approaches. The first tool we studied in clinical and sensor-based approaches is the vibrocital test and thermal acetiometry. This process tests sensory response in hands, vibration, temperature, etc. But it requires clinical setups and prior symptom reporting. Then we move on to part 2 pegboard grip force test. It measures dexterity and hand strength, but it is useful only when symptoms are visible. After that, we move on to cold provocation test. Cold provocation test detects vascular heart symptoms under cold exposure, but it's not suitable for frequent or real-time monitoring. That's we need. Then we move on to traditional clinical diagnostic pathway. In traditional pathway combines history, physical exam, and specialized test, but long delay is expected from symptom onset to official diagnosis, and it usually ranges from 3 to 9 years. Then we move on to smartwatch based vibration monitoring. It uses smartwatch sensors to measure tool vibration, but it measures, the problem is that it measures only tools, not workers, and suffer from environmental noise as with all sensor based systems. Now, after that, we move on to hand-down vibration database. This database compares real-world tool vibration versus manufactured data, but it doesn't assess worker condition and symptom onset. Now we'll talk about machine learning based approaches, AGL system, tool classifier, or both work on tool interaction, not on physiological impact, and they are not suitable for medical assessment or field evaluation. Credo Labs by lay summary, it's a more informative study, no actionable tool and method is proposed there. Now we finally move on to our proposed methodology section. Our proposed system is a three-module deep learning-based pipeline. The first part of this pipeline is HYPE's whiteboard interface, which collects drawing data from the users. It collects XY coordinate and timestamp from the user and passes it to the second stage of this pipeline, which is shape detection model. The purpose of this model is to filter out any shape other than wave or spiral. For this purpose, we used a fine-tuned MobileNet V3 model. Then filtered out drawings are fed to the hubs detection model. It detects whether the drawing is for hubs or healthy based on drawing data. For this purpose, we also use MobileNet V3, a large model, but it was fine-tuned, not Parkinson data. Now we move on to our experimental setup section. Our experimental setup section is divided into two parts, datasets and model architecture. As I have mentioned previously, there is a symptomatic similarity between Parkinson's and Hubs. That's why in this experiment we used Parkinson dataset from Frontiers in Neurobiology by Professor Zam and his colleagues in 2017 as a proxy dataset. This dataset is publicly available and consists of spiral and wave drawings. We used in this experiment 70% of the images of the dataset as training data, and while 30% were used for testing. We applied image augmentation, blur, pixelation, noise, and dark light variation for augmenting the images. After datasets, let's move on to the second part of our experimental setup, which is model architecture. Both of our models, shape detection and hubs detection, use MobileNet V3 large as the base model. The reason why MobileNet V3 was selected is that it's a lightweight model, so it is perfect for deploying to resource constant edge devices as well as at the same time it provides very high performance. Both of these models were fully fine-tuned for their respective tasks using transfer learning, and they were implemented using PyTorch and trained on NVIDIA RTX 46 ADA 00 ADA GPU. Now let's start our results and overview section. The first thing that comes when we are discussing about results is that evaluation matrices. In this experiment, we use confusion matrix, accuracy, precision, recall, and F1 score as our evaluation matrices. The first evaluation matrix here we'll talk about is the confusion matrix. Here in this experiment, we use category specific confusion matrix. From the table, we see that the shape detection model for the both healthy and hubs data produced near perfect accuracy by classifying all the examples correctly. Well, for the hubs detection model, for the wave drawings, the model performs very well with around 90% accuracy, providing 10% misclassification. But the model's performance decreases a bit for the spiral waves, where it misclassifies 25 healthy spiral data as hub disease data. Now we will talk about other matrices. For the hubs detection model, it performs very well for the wave drawings, where it produces 93% accuracy, 93% precision, recall, and overall 93% F1 score, projecting a solid performance. But its performance decreases a bit for spiral data, where its accuracy drops to 83%, precision to 82%, and finally F1 score to 84%, which is a significant performance decrease. But for the shape detection model produces near perfect accuracy for both healthy and hubs data, producing 100% accuracy, precision, and recall score in both cases. Now finally we'll start our results and discussion section. Our system proves the efficacy of deep learning based approach with impressively high performance. It also demonstrates the Parkinson's data's usability for detecting hubs. The lightweight MobileNet V3 model provides impressive results on shape and hubs detection, as can be seen from the matrices I have discussed previously. False prediction that mostly occur with spiral inputs, indicating the need for better feature extraction. So a better feature extraction is needed, we can observe from the experiment. The selection of MobileNet V3 makes the system lightweight, as I have mentioned again and again, and suitable for use in construction environment and mass deployment. The collecting real hub specific data is essential to improve models accuracy and generalization. Finally, we move on to our conclusion and future work section. In conclusion, we can say that our proposed tool shows efficacy of variable independent deep learning hubs detection approach, which we wanted to do in our research work. We created a lightweight, easily deployable system useful for mass use and mass deployment in construction area, and construction workers can use it without minimal training. In future, our plan will be to decrease dependency on Parkinson data, which we use here as a proxy data set, and by collecting real-time hubs data. In future, we will try to incorporate additional features, additional drawing features, which are pen pressure, drawing speed, pen tilt, etc. And we have planned to deploy and test that tool on set in real construction environment by creating a mobile or tablet-based app for field use. Here are the references that we have used in our presentation, and that finishes our presentation. Thank you all for your attention.